Welcome to the next video in a course in discrete mathematics. This is lesson 8, discussing the solutions to the propositional equivalence exercises. So in this exercise, we were going to decide which of the following are tautologies, contradictions, or contingencies. Truth table, very simple truth table, would demonstrate that this is a contingency. It has a row at which it is true and another at which it is false. This is a contingency. I won't necessarily go through the truth tables, so I'll just say contingent. The truth tables, I think by now we've done enough of them for that to be clear. I'll just say that this is a tautology. This is a contradiction. This is a tautology. Now, this is one where the truth table might take a while, and it might be worth just thinking about how we could take a little bit of a shortcut in this particular case. And here you might think, well, let's try our best to make this proposition true and see if we cannot, making the most generous choices along the way, if there just is no possible way of making this proposition true, then it must be a contradiction. We're going to sort of see how that kind of argument could go. If we're going to try to make it true, then we're going to have to set Q equal to true. And we're also going to have to set P equal to true, because if we did set either of those to false, this conjunction would evaluate to false. Having made those choices, we have to make them consistently throughout. So Q, we can label as true everywhere that it occurs, likewise for P. We then are forced to compute this negation as having the value false. And now this conditional has true in the antecedent, false in the consequent, and evaluates to false. And now this means that the entire proposition has evaluated to false. And there's a demonstration that this must be a contradiction because, well, in short, the argument that we just gave basically demonstrates that any assignment of values to the variables will cause this to evaluate to false. Now here, we're going to decide whether or not the following are equivalent by building a truth table for each. Now this first one, I actually believe I did a truth table for exactly this in a previous video, and we found that these are not equivalent, so I'm not going to go back through the truth table there. In the next one, there is, as advertised, a bit of a gotcha here. Now we're going to try to decide whether or not the left-hand proposition is equivalent to the right-hand proposition. But what is this right-hand proposition? We have to read with order of operations, and that means that we have to read P conjunction Q as binding first and only later reading the conditionals. But then that introduces the problem that we have a conditional, without parentheses. We talked in a previous video about how if you have any chain of conditional propositions, you have to use parentheses to disambiguate the order in which the conditionals are meant to apply, because you get different truth values if the parentheses are placed in different places. Well, here there aren't parentheses, right? We've got this proposition, this proposition, this proposition, and no parentheses to tell us which order the conditionals are meant to apply in. So this is actually meaningless. The right-hand side is a meaningless expression, and it cannot have any truth value. So in fact, it is even meaningless to talk about whether or not that is equivalent to anything. But this last one is possibly more interesting, and maybe it is worth actually doing this truth table just to see one of these. So let's go ahead and write the truth table for this. We're going to generate all possible rows, which is going to involve these 4 rows. And we're going to have to build up these propositions in order. So if I look for all of the order 1 complexity propositions, I see that this is one, so we're going to write down P or Q. I see another order 1 proposition here, so that's P and Q. I see another order 1 proposition here, which is P, O plus Q. So there are all of my order 1 propositions. Let's go ahead and write down all order 2 propositions. So here is an order 2 proposition. There are no others. So we look for order 3 propositions, and there's going to be an order 3 proposition here. So let's write that down. And finally, we need the biconditional between the two sides, which is the next most complicated proposition. So we'll write that down next. And now we're ready to start filling in some truth values. Oh, I need parentheses there. So to begin with, the disjunction has true everywhere except where both propositions are false. Conjunction is false everywhere except where both propositions are true. And these are true when there is a mismatch between the truth values. In the next column, I negate the conjunction column. So we get false, true, true, true. In this next column, since things are getting a little bit spread out, I'll go ahead and just annotate all of the values coming from the disjunction column and from this most recently computed column. Those are going to determine the values that we use to compute here. So we're going to get false, false, or sorry, true, true, and false. And here I've annotated the values that come from the first column, so that gets us all of these. And I've annotated the values that come from the O plus part, that's all of these. So now we have the values to compute, and these will evaluate to true when there's a match, and that in fact happens at every row. And since this is a tautology, then therefore these two propositions are equivalent. And finally, we have these proofs of equivalence by chaining known common equivalences. So this is where there's really something pretty new. So we'll really do these in detail. We start by writing down the left-hand expression, proposition, and then start applying known equivalences until we reach the desired proposition. In this particular case, it seems like a natural guess to go ahead and use distribution to distribute P into this disjunction. So we are going to get P conjunction negation P. That is sure to turn into something nice. Disjunction with P conjunction Q. And since P conjunction Q is the target proposition, this is probably a good move. This is, we'll justify this by the distribution rule. So as we observed, something nice happens here. In particular, we apply the negation equivalence to say that that is equivalent to a contradiction. And probably we're already suspecting that we want to use one of the identity laws to basically drop the contradiction in the disjunction. But if you study the identity law, the contradiction has to occur on the right, and since we're being very precise about using all of our justifications, then we first have to use commutativity to move the contradiction over to the right-hand side, and then we can use the identity law to drop that contradiction, and this was the target proposition all along, and so we're done. So next we'll move on to problem number 2. We'll start by writing down the left-hand side. And as usual, when we have a conditional proposition, one of the first things we tend to reach for is the conditional disjunction equivalence. So that gets us this proposition. A natural guess as to a next thing to do would be perhaps to distribute the negation into this. The name of that justification is De Morgan's law. And so we are here. Now, it seems perhaps intuitive that if we could get the negation p and the regular p together, that we could do something nice with those. To get them together, though, we have to kind of switch things around. So I'm going to maybe start by using commutativity on the first disjunction. And so swapping things around brings the p and negation p closer together. That's a nice thing. We also want to group them into their own parentheses, so we'll use associativity to do that. Now that it's here, well, if we studied right, I think we know that we're going to use the negation laws to say that this is a tautology. Now, to do that, notice that the negation has to be on the right-hand side of the disjunction, whereas here it's on the left. So we need to switch things around. We'll do another step of commutativity for that. So having applied the commutativity, we are now in a position to do as we planned, apply the negation law. And at that point, we have a tautology in a disjunction. So the domination law says that the result is equivalent to a tautology, and we're now done. So next, let's talk about the third problem, which is this equivalence. So we'll start by writing down the left-hand proposition. As usual, we jump right into applying the conditional disjunction equivalence. Maybe we'll do it in 2 steps, although perhaps in theory we could do it in 1. But just to make sure that we're tracking everything that we should, then we'll do this. So that's 2 steps of conditional disjunction. Now, if we look at the thing that we're trying to prove, right, it's often, in a few of these, you can kind of get away with just being a little bit on autopilot and just doing natural steps. But sometimes you really need to think about where this particular challenge is trying to lead toward. And we can see that the P and Q are packaged together in the target proposition. And so we probably want to apply associativity to put P and Q together like that. And in fact, maybe we even want to pull the negation out of that so that we're not talking about negation P, negation Q. And the rule that justifies doing that is De Morgan's. And at that point, we're very much primed to reach the end, because this now just kind of looks like the picture of the conditional disjunction equivalence. So we take the negation away from that left proposition and use a conditional, and we have exactly the target proposition, so we're done. And I'd like to end the video on an invitation to ask questions. So if you found anything confusing in this video or the associated portions of the textbook, please leave a question in the comments. I may address it there, or if it's complicated enough, I may make a video and include it in the playlist.